Hello guys, welcome back to the rest of the solar system. So what we've talked about are the gas giants, we've talked about the terrestrial planets, we've talked about the various moons around the planets, and so now we're going to talk about everything else that's in the solar system. And the other thing that we're going to talk about is why Pluto is no longer a planet. I'm sure when you guys were in elementary school or junior high, you learned that there were 9 planets in the solar system. Well, there's actually only 8 right now. So how can Pluto get demoted to a dwarf planet? Well, in 2006, the International Astronomical Unit, which is basically the governing body for astronomy, defined criteria for identifying and classifying objects in the solar system. Wasn't a popular decision, and lots of people are still arguing about it, and there's, a chance it may change, but I doubt it. So one of the things that they were doing is trying to define exactly what a planet is. We're finding so many things in the solar system as we get more telescopes out there that are orbiting and that are heading out through the outer part of the solar system. So we're having to come up with new classifications. And unfortunately, when they came up with those new classifications, if you are a real Pluto fan, Pluto did indeed get demoted to a dwarf planet. So guys, let's go ahead and start talking about comets and asteroids. Now the reason that we like to go ahead and look at this is because we believe that comets and asteroids are that primitive material, that material that really has not undergone any kind of chemical change since the beginning of the solar system. So that means if we can get our hands on an asteroid, or by the time they get to us, meteorite, then we can look at the material that our solar system itself was made out of. So an asteroid basically is a small rocky object containing little volatile materials. Now guys, the word volatile simply means that it has a very low boiling and melting point. And so if you think about rubbing alcohol, I put some rubbing alcohol out on a table, then that rubbing alcohol is going to evaporate very quickly. That's an example of a volatile material. Now here you have a star field, and notice that little line that went zipping through there. Well, that was then, there it went again. Then that was a little meteorite that was in our atmosphere that you're looking at. Most asteroids are found in the asteroid belt, generally between Mars and Jupiter, which means we're about between 2.2 and about 3.3 astronomical units. Remember, an AU is simply the average distance the Earth is from the Sun. And when they were first discovered the first asteroid, they were actually looking for a planet. And the first asteroid was discovered in 1801 by the name of Ceres. And so we still go ahead and follow it today. And it was originally named for a goddess, and then women, and then people, and now numbers. We've got so many of them. Now this picture is showing you the near-Earth asteroids as well as the asteroid belt. And it's a little bit hard to kind of look at to start with and realize what we're looking at. But that very center is the Sun, and then you'll have these blue circles as we're moving out from the center, and so that's Mercury's orbit, and then of course Venus, Earth, and Mars. And then we see this massive amount of green stuff, and those are then the asteroids that are between Mars's orbit and between then Jupiter's orbit. And then you see those red objects, and those are what are called near-Earth asteroids. So those are asteroids that get tracked because they're coming very, very near the Earth, and occasionally one of them, will go through the top of the atmosphere, or sometimes we actually have them hit the Earth. Now, there are 2 moons of Mars, and they're probably captured asteroids. I like to think of them as kind of looking like big lumpy potatoes. One of them is Phobos and one of them is Deimos. And Phobos is probably going to run into Mars in the very far future. I mean, it is getting closer and closer and closer. And so these are just the 2 moons of Mars, and you can see, being so close, somehow those little asteroids probably got perturbed out of their orbit a little bit and got close enough to Mars, and Mars then went ahead and captured them. You can see they really kind of do look like lumpy potatoes. So now let's talk about some classification of asteroids. The first type is a C type. And about 75% of the asteroids that we see out there, are the C-type asteroids. C stands for carbon, and the asteroids are very dark with a reflectivity of about 3 to 4%. Again, think of that kind of lump of coal that you would have out there, how dark it is. And so we do have a lot of silicates and a lot of then carbon in those C-type asteroids. Then we've got the S-type, and those are basically stony types. And so they've got a much higher reflectivity, about 15 to 20%. Think of a C-type and take out the carbon, and you're going to get an S-type, about 17%. So basically stony material that you're kind of used to thinking about. And then the rest of the asteroids out there are what are called U-type. At one type they were called the metallics, because basically they're made up of a higher percentage of metals. And so they have an extremely high reflectivity of about 60%. But you can see that there aren't very many of those U-type asteroids out there. But when you look at those things, they are very distinctly made of metal. Composition, like I said, C-types are certainly primitive material, composed of silicates, which is what we consider the rocks, with that dark organic hydrocarbons. And like I said, guys, these things are chemically unchanged since the beginning. So that means, these were there when our solar system started, and if we can look at them, we can get some evidence in what our early solar system was like. S-types, like I said, are those stony asteroids. Basically, they don't have the carbon compounds in there. And they are also considered then to be primitive material. And then those U-type, they really don't fit either the S or C. They used to be called the M-type for metallic, but now in general those are all the other asteroids that don't exactly behave themselves as either a C or an S-type asteroid. C-types are found in the outer part of the belts, and the M-types tend to be a little bit closer. And it's probably due to differential settling of that planet material. Were the asteroids maybe a planet that didn't quite make it? Was it a planet that broke apart? Not exactly sure. But remember, differential settling just means settling based on a difference in terms of densities. Now remember, the first asteroid that was discovered back in 1801 was Crees. It has a diameter of approximately 975 kilometers. Okay, guys, remember that 1 mile is about 1.6 kilometers. So that kind of gives you a rough estimate of what the diameter of this thing is. It rotates every 9.1 hours and revolves in around 4.6 years. Density is about 2.2 grams per centimeter cubed. So it suggests that it does have a rocky core, probably surrounded by some kind of water ice. Because remember, guys, we have a density of about 5.5 grams per centimeter cubed. So if the fact that it's less dense than what we are, it tells us it probably doesn't have that really large iron core. And so it makes more sense then to have a rocky core surrounded by kind of this water ice layer with maybe a thin, dusty outer layer. And it is the largest asteroid within the belt, which makes sense because it's probably why it was the first one we actually discovered. And this is a picture of it taken in 2004. You can see that it has a little bit of a different shape. It doesn't look exactly like a lumpy potato like what Phobos and Deimos look like. And so it's a little bit more of a structure than what you have of those other two. That's not going to be true of all the asteroids that we see out there. Then we have Vesta, and it's also one of the larger asteroids. And it's brighter simply because it is closer. Its surface is covered with basalt rock. Now, basalt rock we have an indication of volcanism. So we do think that at one point Vesta did have some volcanoes going off, probably not in the traditional way that you think of volcanism with these big cones, lava spewing out from the top, but more just from the fact that the surface cracked open and you had lava then that welled up. And we do think that's short and very intense. And at this point, guys, if we have then an asteroid that does have that volcanism that's gone on, that means it has been heated, and so that means that original primitive material has undergone some changes. Direct interaction with its surface has shown that it could not have come from Earth, and we've actually got some of that asteroid here. And the fact that it's about 4.4 to about 4.5 billion years old. And that makes sense because we think that the solar system is on an average of about 4.7 billion years old. So that date works out really well. This is fragments of Vesta. Remember I said direct interaction with its surface? By looking at this, and by looking at where we found it and looking at the chemical composition, things like that, we think that it is certainly a fragment of Vesta. Notice it was taken in 1995. If you're going to find asteroids, the best place to look is going to be the Arctic or the Antarctic, because you essentially, once they get in there and they get frozen within the ice and they don't undergo any kind of change because of what's going on within the Earth itself. So they're that pristine material when you go ahead and dig them up. There's other kinds of asteroids out there. There's Ida, which is an S-type. Remember, that means it's made of stone. It's about 35 miles in length. It does show some weathering. It has its own moon. We didn't think that these little asteroids would actually have their own moon, but yes, we find that that's kind of common. Then we have Gaspra, which is also an S-type. It's only about 200 million years old, so we think that it was probably formed in a collision, and it's only about 10 miles long. And because, you have this really large concentration of asteroids, they will run into each other. And so when that happens, you will have collisions. You'll see that you've got some of those surfaces that look like they have impact craters on there, or they look like that they have certainly been broken apart. And that's because they probably have. And then Itoka, and I wouldn't swear that I pronounced that one right, is about 2 kilometers long, no craters. It kind of looks like it was pretty well smashed together. It just gives you a feel for what some of these asteroids look like. You can certainly see that there's evidence, it's certainly on this one, of impact craters. Color on this one, false color guys to go ahead and bring out the different characteristics of the surface itself. A lot of them do not have any kind of nice round circular shape. This is the one that kind of looked like it's smashed together. It does not look like the other asteroids, but it's much, much younger at this point. And it does have a different appearance. It just looks like all those rocks have been smashed together. And then, like I said, the near-Earth asteroids were those ones in red that I showed you. And so we certainly do go ahead and plot the orbit of those to know if we are going to have any of them coming near. And every once in a while you'll hear, the doomsday because, hey, this thing is coming toward us. By the time it usually gets to us, it's not really going to hit us. Sometimes they come pretty close. And sometimes they will go ahead and run into a planet. So are they coming? Certainly. What do we do about that? Unfortunately, we don't have the mechanisms they show in a lot of the movies about being able to blast them out of the sky or go take a spacecraft there, put it there, and basically nuke it to death. That's not going to happen, guys. We just don't have the technology to do that. It looks really good in the movies, but it's basically Hollywood. They can run into a planet, or they can be ejected from the solar system due to the fact that they've had a close encounter. And so we, like I said, do go ahead and track these. And this is one where we were actually going by it, and so we actually got to see it moving and rotating in space, which I thought was kind of cool. And this is one of the flybys, and you can see this was taken in 2000. And so every spacecraft that we send to the outer parts of the solar system have to go through the asteroid belt. Now, that was one of the things at the very beginning when we started sending probes out there. Could it make it through the asteroid belt? Was it going to be so thick that, going through the asteroid belt, we wiped out our spacecraft, and we found that wasn't true. The distances are still great enough between those asteroids, it's not a problem. And then meteorites are those space rocks, basically, those asteroids, that have hit the Earth. And usually they're much smaller than a typical asteroid, so that means they've broken apart. And that means they're moving a little bit faster than what the asteroid itself is that they came from. They can also come from Mars. We know that we've got that rock that I showed you before from Mars. By looking at the chemical characteristics, we know that it probably got kicked up from either a volcano or something like that and made its way toward the Earth. So there's lots of stuff out there, and if it happens to get close enough to the Earth that it gets drawn in by the Earth's gravitational field, then it'll eventually come down. Now, just look at this picture, and I know it's probably very hard to see, but I still wanted to go ahead and leave it in. And I will give you the URL for this picture, but all those little dots in there are meteorites that have been observed as they've been coming in through the upper part of the Earth's atmosphere. Now, you'll also notice that there are labels on some of them. You know, the Lyras, the Leo, Hydra, Gemini, Orion. And those are meteorite showers, which we will talk about. And so that's why you see a lot of those really large number of strikes, is because of the fact that we are going through a meteorite shower. Like I said, the best place to find them, guys, is the Arctic or Antarctic. Nice pristine conditions out there according to the weather, because you essentially don't have any weathering and erosion out there. And this is just a picture of an asteroid when it is in the form of a meteorite coming through the upper parts of our atmosphere. And it will rotate a lot, certainly going to heat up. If you happen to actually see see a meteorite that actually comes through the upper part of our atmosphere, and you're lucky enough to go ahead and find it, first of all, don't touch it until it cools off, but certainly record when you saw it and exactly where you found it, because it's very important information. So just some examples of some asteroids. I'm stuck on the word asteroids this morning. Some meteorites that have made it to the ground, and we're lucky enough that they were again observed, or based on the densities, the feel, the texture, you can tell that these things were a rock that did indeed come through our atmosphere. Now look at this one. There was a lot of outgassing. So when they come through the upper part of our atmosphere, they're going to get heated up. And so if you do have a lot of gas in there, that gas will go ahead and come out of solution. And when you pick them up, they're going to just feel differently. They're also, and you're going to look differently. This is not a rock that would have been produced here on the Earth through weathering and erosion, things like that. You're not going to see this. This definitely looks like it was heated. And that's why you get all this outgassing in there. And of course, this is a meteorite that you saw earlier. We were talking about Mars. Just another one. Again, look at the holes in it. I mean, it really does look a little bit different. It looks like maybe it was heated, just appearance-wise, a little different than what we see here on the Earth. Now, a lot of times what they will do is they will take slices of these and go ahead and look at them under a microscope, and you'll find that they are polarized. And so that polarization then gives a feeling for the structure of the chemicals that are making up this meteorite. Just another one. I know this is a little kind of fuzzy, but I still wanted to go ahead and keep it in there because this also then gave you the feel for the size of that. Remember I said that when you look at those metallic ones, those U-type meteorites, or asteroids at that point, which is then becoming, they just look different. I mean, if you look at that, that looks like a metal. And you've got all these scrapings on it, things like that, and that has been sliced there. And so this is what the inside of that U-type asteroid looks like. Now, how do you like the size of that one? That one would have put a significant hole in the Earth. But you can see that it looks like it's been heated, all those outgases. A lot of that material then, when it came to the upper part of our atmosphere, did get heated and then just went ahead and left. Probably don't want that thing to go ahead and hit your house. Just another one. Notice how dark this one is. I think that little boy there looking through that is so cute. It's like, what do I see in there? That's another one. And that's another really large one. Now, they do at times come through objects, come through things that are on the Earth. And so this one did come through somebody's roof. You know, is your insurance going to cover that? Probably not. They consider it an act of God. So chances are, if you have some kind of meteorite come through the top of your roof, probably not going to go ahead and be able to collect on it. The ones that came through here, came on down, ran into, this is actually out toward like a little utility porch. And notice, guys, that put a pretty good sized dent there and then bounced off and hit the ground. Now, this lady is standing in front of her car, and notice the side of her car. That front fender there, that front headlight, well, that thing was smashed by a meteorite. It looks like it was crumpled, but in reality, it was smashed by a meteorite. That car just happened to be at the wrong place at the wrong time. But notice she's smiling because she knows exactly when that happened, and she has a little piece of rock that came from that. And then, this is Michelle Kapp, find a new way to get around for a while thanks to a 30-pound meteorite that slammed into her parked car, passing right through and leaving a small crater underneath. So, yes, that thing, they know exactly when that thing hit. And a lot of times you are going to have every year these meteorite showers that keep coming back every year, and so you pretty well know when they're going to be. And if you go outside, usually between 2, 4, 5 o'clock in the morning when they're coming in, you know, some of them you can have 10, 15 an hour. Some of them you can have 10 to 15 per minute. I've had the great opportunity one time to go see a meteorite shower, and we took a big boat out in the middle of Table Rock Lake. Completely and totally dark, and you looked up and here were all these incredible meteorites coming down. Guys, if you ever have a chance to see a meteorite shower that way, take advantage of it, because it was absolutely phenomenal. There's all kinds of these. Midnight sky flashing eerie blue early Thursday over 4 Midwestern states as a meteorite exploded in the atmosphere. Well, these are big fireballs. These are not necessarily associated with any particular shower. They just happen to go ahead occasionally and hit. He was examining dozens of pieces of meteorites and plotting them where they fell. The largest he saw was about 7.5 pounds, which is a pretty good size chunk of rock coming down. For me, it was a dream come true, he said. I always tell my wife that when I die, I hope I get hit in the head by a meteorite flying through the roof, and it came pretty close, he said. So, like I said, if you've got somebody that, in this case, this man was a professor of geology and astronomy, being able to see one of these fireballs, and then to be able to not only see it, but then to be lucky enough to be where it was coming down, is quite an opportunity. Now, we also know that we have these meteorites that are hitting the dark side of the moon. And just here's some examples you can see on the left side of the moon where those meteorites are hitting. So we do know that they're still out there, that they still run into a variety of objects. And when they do, there's little impact craters. And then we have, like I said, these fireballs, and they are meteorites that are very large, and they make a very bright path across the sky. And a lot of times when you go outside and you see them, you'll say they appear to be right overhead, but in reality, a lot of times they will pass over 5 or 6 states, and so you'll get a big track as it comes through the sky. This is just a picture of a fireball. They're big enough they can go ahead and break up as they come through. It's an extremely impressive sight. It happens to be the northern lights with a big meteorite fireball coming through. And here's one that was captured as it was coming through. Notice how bright it gets, and then it'll go ahead and fade back. This was taken in November the 18th in 2001. Remember, there's a tremendous amount of heating due to the friction when they come through the top part of our atmosphere. And so they're going to get heated that way. And a lot of times that's unstable heating because they're also very, they're not symmetrical. And so a lot of times what happens is they will go ahead and break apart. This is another fireball. Can you imagine looking up and seeing that come over your house? I mean, now that's called breaking apart and really coming in as a fireball. And then the impact craters. And guys, these impact craters are from these meteorites that are much larger than, the normal ones, and they can make a really big hole in the earth. Have you ever been out to Meteorite Crater in Arizona? That's probably the most famous one that we've got, certainly in the United States. I mean, look at the size of that hole. And the fact that it's out there in the desert, you get very little weathering and erosion. And you can see the road up there on the right where you can actually drive out to it and get down and walk around it, things like that. But that was put there by a big impact crater, probably a meteorite, that came from the asteroid belt, wandered close enough to the Earth, and got pulled in. This is a very, very old one that's actually fossilized. You can kind of see where that one hit. Once we got our satellites up where we could start looking down on the Earth, it was amazing how many impact sites we actually found. This is up in Canada, and you actually have one that came in right beside another one as it broke apart then, and then filled in. And so these are actually very nice-sized lakes. It's another one that the middle of it you can see is still there, but the outside simply filled up then with water. Now, we think that 65 million years ago, we also had an impact crater. And you can see there that it came through. Obviously, guys, this is an artist's conception. But that's when the dinosaurs were probably wiped out. Now, is this infinitive, the way that the dinosaurs were wiped out? Absolutely not. But the timing certainly is very suggestive. About 65 million years ago, something happened. Wiped out not just the dinosaurs, everybody just talks about the dinosaurs, but it wiped out a number of other species, as well as plants, things like that. Now, the question is, if this happened, would we be able to find out where it happened and where did that actually hit? We think that it hit in Mexico and down then right outside that Yucatan Peninsula. And so this is actually the impact site. It's now covered in water. That we think was the meteorite that did indeed wipe out and have that mass extinction about 65 million years ago. Luckily, things like this do not happen that often. I mean, this was a world-changing event. You certainly don't want those to happen very often. And then we have, besides asteroids, which then can become meteorites and run into a variety of things out in the solar system, we have comets. And comets are small, icy pieces of material containing frozen water and a lot of other volatile materials with solid grains mixed in. Now, that description in no way, shape, or form does justice to a comet if you look out and see it in the sky. They are phenomenal. And again, guys, if you ever have a chance to see a really big comet, a really bright comet, take advantage of it. That will be one of those things that you will remember. Comets are found basically in two main places in the solar system. One of them is the Kuiper Belt, and that's a little bit beyond Neptune's orbit. It's about 45 AUs. And these comets that we find in the Kuiper Belt are very short period comets. By short period, we mean something that has a period less than 200 years. Think about Halley's Comet. You know, it comes back around every 76, 77 years. Okay, so those are short period comets. And then we have the Oort cloud, which is much, 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 much further out. That's about 50,000 AUs. You know, so we're an appreciable amount or distance between here and the next star. And those are very long period comets. You know, if we see one of those comets come in, chances are we'll never see it again. First of all, we're never going to be around that long. And the other thing is just the fact that they also may head out of our solar system as well. And the way that they get inside, the way they get sent toward the sun is there's lots of things out there that they get jostled about. Well, if they get jostled enough and they get kicked out then toward the center of our solar system, then they'll start in, and sometimes they will get captured by a planet's gravitational field, or a lot of times they will get captured by the sun's gravitational field. We know comets have been observed from the earliest times because there's all kinds of recorded historical events that have talked about the comets. And you know, some people think those comets are good omens. Some people think they're bad omens. It just kind of depends. Most comets, though, we know are not visible, and so therefore we never go ahead and see those. So now let's talk about what makes up a comet. Well, I've got kind of two pictures here. And notice which direction is to the sun, and that's going to become very important with one of the tails that we're going to talk about. So you have the head of the comet. I'm just looking at that comet in space. You've got the head of the comet, and then behind that comet you have an incredibly long tail. It can be about 100 million kilometers. Well, guys, that's about 60 million miles. I mean, think about that, guys. We have a tail that's 60 million miles long. And so that's what you see when you see a comet. You see the head of the comet, and you see this incredible tail that's behind it. Well, if I go ahead and I look at what makes up the head of that comet, then you see that very, very, very small center. And the head of the comet contains the coma, which is kind of the inside where I'm looking at that icy nucleus. It's typically, 1 to 10 kilometers in diameter, which is about 0.6 to 6 miles. It then goes ahead and starts evaporating due to heating by the sun, and that's then when you get that coma that's going ahead and forming. And that coma can be, approximately, again, up to about 60,000 miles. So that seems pretty good. And notice in that picture on the right, you get that gas and that dust, it gets swept back. Well, that's getting swept back because of the solar winds from the sun. And so we're going to find that there's two tails. There's an ion tail, and then there's a dust tail. And the dust tail and the ion tail are two entirely different types. One of them's made out of a lot of gas. That's what that dust tail, or the gas tail is. A lot of times, too, that's called an ion tail. So you'll see an ion or a gas. And then, of course, the long one, which is made out of the dust. Well, and then surrounding the coma, which is transparent, we can't see that part, is going to be this hydrogen envelope, which is made out of basically hydrogen molecules, hence the name hydrogen. And so it's about 10 million kilometers across, or about 6 million miles. And we can't see that. So basically we have that head, which is made up of the actual nucleus of the comet itself, and then the coma, and then you have this incredible tail. So nucleus is a relatively solid and stable, and that's generally what's there all the time. It's mostly ice and gas with a small amount of dust and these other solids, and those can include hydrocarbons and silicates. Now, guys, hydrocarbons means that we've got hydrogens and we've got carbons in there. And notice that we also have ice. Well, if I think about it, those are certainly the materials that we need for life. We need water, we need hydrogen, we need carbon. So that material is there and has been there because comets are considered to be primitive material. We also think that the fact that there's water in there, that might have played a significant part with producing water in the early parts of our solar system when these things ran into the planets out there. This is a typical nucleus. Notice that it's got bumps in it, it's got protrusions in it, it's got areas that look like they've been outgassed. Remember that these short period comets generally come around a lot. They come back periodically, and every time they come back, that material is getting lost because of the outgassings. And so eventually what will happen, and those will go ahead and eventually break up. Nucleus, like I said, less than about 30 miles across typically. And the nucleus itself will typically be some of the darkest objects in the solar system. So that's the other reason that we have a really hard time seeing them before they actually start all their outgassing. And so they will end up coming in toward the center of our solar system, which means they're going to end up coming around the sun. And notice it says the darkness of the surface then goes ahead and helps absorb the heat that's needed to drive those outgassings. What we're going to find is as those things come in and they run into about Mars's orbit on its way into the sun's going to start heating it. And when it does, you're going to start getting a lot of materials that are going to basically evaporate from that comet. And so that coma then begins to go ahead and form. So the coma is that dense cloud of water, carbon dioxide, and other gases that are subliming from the nucleus. Sublimation, guys, means you're going from a solid to a gas without necessarily going through a liquid state. That's certainly what carbon dioxide does. Have you ever played with dry ice? Kind of very fun to play with. A lot of times around Halloween, if you want to go ahead and have a nice fun party and you want to have your witch's brew and you want to drink that, then a lot of times they will go ahead and put dry ice in, let's say the root beer that you're making or something like that. Now, having said that, guys, you do not want in any way, shape, or form drink any liquid that has dry ice in it, because that dry ice is really cold. And whereas it looks really cool, it can do some major damage if you try and drink it. So you can drink it after that carbon dioxide has been dissolved in the water, and you get this nice fuzzy water or fizzy water, and so you got a lot of carbon dioxide in there. And so, like I said, this process of outgassing, of forming that coma, simply goes ahead and starts once you get close enough for the sun to go ahead and really start heating it. And because that, when those gases get formed and they're being outgassed, they have a lot of energy coming up from there. They will carry away, the dust and the gas and things like that. So that's why you're getting that surface forming, or that atmosphere, or at least what looks like an atmosphere forming. And so this is actually Halley's Comet. We sent a probe by Halley's Comet the last time it was here. And you can see which side is lit from the sun, and you can start seeing a lot of those outgassings there and that material that is formed. Now, these things tend to be rotating around an axis, and so part of it will be in dark, away from the sun, then that will go ahead and turn, and so it will be facing the sun, and so you'll get that side. Now, because these things are not symmetrical, there's a lot of, kind of uneven heating, those kinds of things, which can cause some interesting phenomena. Just another picture of that icy core, that nucleus, and then the coma that is being formed from it. And notice it is going in one direction, and that is away from the sun, because the solar winds of the sun will always push that ion or gas tail directly away from the sun. Always, guys. You can always determine what direction the sun is because of the direction of the ion tail. And then, like I said, you get this hydrogen cloud, which is, very, very sparse and which is very transparent for us. This is just a false color kind of showing you the various parts of the comet itself. Right there in the center, you get the nucleus, then you get the coma, and then you get the tail, and then you get that hydrogen envelope around there. Same kind of thing, looking at the center. This one is obviously going sideways because you get some of that appearance of motion in there. And then that dust tail, like I said, guys, dust tail is one kind of tail, and then the ion or gas tail is the second type. Dust tails tend to be the longer ones, up to about 10 million kilometers long, and they are composed of dust, hence the name dust tails, and you're getting that from material that is given off by the nucleus. And like I said, it's certainly one of the most prominent parts of the comet. And if you've got a really bright comet and it's relatively close, that tail can spread over a significant amount of the sky. Back in the early 1900s, when Halley's Comet was here, there are pictures that show that the tail covered about 70 or 80% of the sky. And that's because Halley's was so close when it came back that they actually thought that the tail was going to hit the upper part of our atmosphere. So if you have grandparents or great aunts or uncles, ask them if they were alive in the early 1900s, 1911, when that thing came by. So now, this is a picture of a comet. You see that dust tail is actually curving, and we will occasionally see the dust tail as that comet is moving pretty close to the sun and as it's moving appreciably an amount. You will see that dust tail goes ahead and follows it, but the dust tail hasn't turned quite as quickly as what the head of the comet has. This one, you cannot see that ion tail as nearly as well, and I'm going to show you comet Hale-Bopp here in a few minutes, and you can see the very distinct ion or gas tail compared with the dust tail. But guys, that's what it looks like out in the sky if you're lucky enough to see a comet. Occasionally you have to get up really early in the morning, but I guarantee you that it's worth it. And like I said, there's the eye under the gas tail, and composed of, plasma, which are charged particles. You got rays, you got streamers, and again, it's all caused because of the interaction of the material that is given off by the comet with the solar winds. And so there's more where you're getting your particles, your charged particles, things like that, and that always points away from the sun. So if I've got a comet coming in, and you can see the period of the comet there coming around, or the orbit of the comet coming around the sun, and there's the Earth, well, when I go ahead and look, notice that that tail is always pointed away from the sun. So that means when the comet is coming toward the sun, the tail is behind it. When the comet is going away from the sun, then the tail is actually in the same direction that the comet is moving, because the comet's going away from the sun. The dust tail, the ion tail and gas tail is pointed away from the sun, which means that tail is actually in front of the comet. Now, we're going to talk about meteorite showers. And guys, I want you to look at where the comet is crossing the Earth's orbit. Well, remember that comet is continually giving off material. And so if the Earth then goes through a place that the comet used to be, there's generally a lot of gas and dust there, well, then that gas and dust will go ahead and run into the Earth's atmosphere, and that's when we'll see a meteorite shower. Just another picture of a comet with that really big coma, and it's still developing its tail right now. Just another schematic showing the nucleus, the coma, that dust tail, which a lot of times, sometimes looks yellowish white, and that ion tail will look sometimes very blue. No, a lot of times you don't get that really distinct separation. Now this is actually Hale-Bopp, and you can see the big dust tail there, and you can see the gas or ion tail there. And down in the lower right, you can see which direction then that the sun is pointing, and that then is directly opposite of what the gas tail is doing. This is another picture of Hale-Bopp. Hale-Bopp is one of the brighter comets that has been visible in the last probably 10 or 15 years. Unfortunately, a lot of people didn't go out and take advantage of it. And fortunately, some of you might not have been alive during the time that Hale-Bopp was here. But I can't stress enough, guys, if you have the chance to see a comet, please go out and look. But as we've talked, take somebody you know, love, and trust out there with you. It's a really cool sight. Now, we also know there's a lot of comets that we never see, because remember I said the majority of comets we can't see. But once we had a telescope in orbit around the sun, it's an amazing amount of comets that actually get pulled into the sun. So this is just a picture of a comet heading toward the sun. And yes, it will impact the sun and just kind of get cannibalized by the sun. But they look pretty cool as they go into the sun. There you're looking at some star trails, and you're looking at the center of that comet, and then you can just see around the outside then where that coma is starting to develop. It's kind of hard to figure out exactly where the comet is on this one, because still the process of forming, and you don't really have a whole lot of tail then to go ahead and look at. But I think you can see right there in the center, it kind of looks like a blob as opposed to a nice circle. Well, that's where our comet is. And guys, if you go out and you find a comet, then you get to name that comet whatever name you want. And in fact, most comets are not found by professionals. Most comets are found by amateurs. I mean, there's some student in, I think it's either Japan, I think it's Japan, it could be China or Japan, that has a huge number of comets, to his credit. And he goes out basically every night and looks for a comet. And he's still discovering them. This one you can see is developing that coma. And you also see some really cool nebulous material then on the right. You obviously have no problems picking that comet out. It's coming directly toward us, it appears like, so that you're not seeing the tail. You're just seeing that coma head on. And a little bit of indication of where the nucleus is itself. Just some pictures of some comets. This one you certainly see has a really nice tail developed. You can kind of see both that kind of yellowish, whitish, and then you can see that blue tail. This was kind of weird, this one, in the fact that it had a really nice coma develop, but it never really developed the kind of tail that you normally would have expected. It's always kind of a wimpy little tail. This is kind of the picture of the one I showed you earlier. This is Comet West. This one I had a chance to see. And it was so cool. I was coming back one night real early, and I have a little tracker, and I had the roof off the tracker, and I was out in the, coming back from Cassville. Just gorgeous skies. The roof was off my car, and there was this incredible comet. I thoroughly enjoyed the drive-in that night. Just a variety of pictures of comets. This is a comet of 1882. And so this is a drawing on how bright that comet was when they saw it. Obviously, it was very close to the Earth, probably on the same side of the sun as what we were. One taken in 2002. This is the one I was talking about earlier that never really developed that really nice tail. I mean, it was still cool to look at, but just didn't quite have that tail out there. Now, big misconception is the comets go zipping across the sky. I mean, because that's how they always draw them, a comet going zipping across. Guys, they don't do that. I mean, they're going to move. But they don't go zipping. And generally they're visible for, a couple of weeks, depending on where you catch it. And you can see it both when it comes, hits going around the sun, so you can usually see it on both sides. One obviously is going to be much better. It depends on where we are. It's another comet. Most of these guys are not time exposures. I mean, they are a little bit to go ahead and bring it out. But most of these are just what you look at when you see it in the sky. This is Hale-Bopp. And so you see that really nice ion tail, then the gas tail, then the dust tail that's right below it. And you see them just kind of in various positions within the sky, depending on what's going on. Where are they in their orbit around the sun? Are they going around? Have they been coming back and they're all on the back side? Just kind of depends. So let's talk about the fate of a comet. Certainly it can break apart and continue in its path. I'm going to show you one that did that here, that ran into Jupiter. It can impact a planet if it gets too close. We think we might have had a comet hit us in the early 1900s. Just looks like something broke apart right above the Earth. And when I'm talking about above the Earth, I'm talking about almost right above the Earth in Tunguska. If you go back and you look and read some of the information about the Tunguska event, we think it was probably a comet. It certainly didn't go ahead. We don't think that it was a meteorite because there was not really an impact crater like you would have expected. It can certainly speed up. If it gets too close to a planet, it can certainly speed up. If it gets close enough, let's say the sun, to go ahead and speed up, but it doesn't get close enough to actually get pulled in, that gives it a little bit more speed, and so therefore it can be ejected out of the solar system. Or it can be perturbed into an orbit with a smaller period. All of those are the fates of comets. This is a comet that actually broke apart. I think you can see all those little bits and pieces. The Shoemaker-Levy comet is the one that broke apart and ran into Jupiter. Now, this is called the String of Pearls. And when the Shoemaker-Levy comet was coming in by Jupiter, it got a little too close to Jupiter. Jupiter broke it up. And what was really cool about this one is that we were able to go ahead and observe Jupiter when Shoemaker-Levy hit it. And man, we could just see every one of those little impacts on the atmosphere of Jupiter. This is an artist's conception. This is not an actual picture, guys, showing what that comet was going to do. Well, now you can imagine that comet then is headed toward Jupiter, and Jupiter is rotating underneath it. So, I mean, man, it was just like dominoes, you know. Once one started hitting, you know, Jupiter went ahead and spun on its axis, and you have the next one that hit in there. And so you were just seeing them one right after the other. Now, this one certainly is what happened. You can see that you have several big holes in the atmosphere, those big dark areas where probably a little combustion, things like that happened. Now, guys, I want you to realize that what you're seeing right there are areas on Jupiter that are bigger than the Earth. So when Shoemaker-Levy hit Jupiter, it put a hole in the atmosphere bigger than what the Earth was. So we really don't want too many comets running into us. This is several URLs that I have, and guys, well, these will be on Blackboard, so you don't need to worry about taking down. But the reason I left them on here is that first one especially is the Tunguska event, which happened in the early 1900s, and I would like for you to look that up and kind of see what it looked like there. It took a few years for us to actually get an expedition up there, but even after a few years, I mean, you can definitely tell something happened. So these are on Blackboard. Don't worry about trying to take them down. I just wanted to refer to these before you actually went there. Now, Halley's Comet is a comet with a very short period comet. It returns about every 74 to 79 years. And we know that it has been doing that since about 230 BC. Because remember, these ancient astronomers recorded things like this. And so we can tell on the average, about every 75, 76 years, there's a comet that's been recorded all the way back since 239 BC. And like I said, that period varies somewhat depending on where we are in our orbit, how close it gets to the sun, how much gas is given off, all those kinds of things. But remember, every time it does go ahead and orbit the sun, material is given off, so that when we then go ahead and run into where that comet used to be, where that tail used to be, then we get a meteorite shower. This is Sir Edmund Halley. Very distinct guy right there. Halley was here in 1835. Absolutely great. 1910. It was absolutely great. My great aunt observed it back. In fact, she was one of them that actually had the chance to see it back in 1910 as well in 1986. And so very few people get a chance to see it twice in their lifetime. Unfortunately, when she saw it in 1986, it was just okay. It wasn't really great. Certainly not like what it was in 1835 or 1910. It will be back in 2061. And so hopefully you'll be here in 2061 and get a chance to go ahead and see it. Then in 1910, when it was here, it did go ahead and the tail actually hit the top part of our atmosphere. And so you look at a lot of the advertisements and all the parties, I mean, you know, having a comet go ahead and get that close was certainly a reason to celebrate. And so when Halley's came back in the early 1900s, 1910, that tail was thought to contain something called cyanogen gas, and cyanogen gas then contains cyanide. And so, you know, you didn't want to go ahead when the tail hit to go ahead and die of, you know, cyanide. So basically they sold comet pills, things like that. Now, guys, you've got to realize that tail is pretty well nothing more than a vacuum. And the fact that hit the upper part of our atmosphere, yeah, there's no way it would have ever gotten down here. But hey, people sold and bought comet pills like crazy to make sure they weren't going to be affected by that cyanide that came through the upper part of our atmosphere. Somebody made a great deal of money on something that it was never going to happen. Like I said, it was also a reason to party. These are some party favors from 1910 when Halley's came through. Go outside and celebrate the return of Halley's. Trying to keep Halley's away. Then there was jewelry that was made that was commemorating the fact that Halley's was here. This is a hairpin with Halley's Comet on it. And then there were all kinds of music that came out. Here's a comet rag. You can see Saturn right there, those kinds of things. Supposedly Galileo looking up at Halley's. Comet ale, drink to, commemorate the fact that Halley's is here. All kinds of advertisement, all kinds of, party favors, all kinds of memorabilia from Halley's Comet. This is an artist's drawing of what Halley's was like when it was here in the early 1900s. I said, guys, I really feel like I missed out. I really wanted to have seen that. But I'm not quite that old. I was not here in 1910. Since both my parents hadn't even been born by that point, it was going to be kind of a problem. But I can remember my aunt talking about it, though. And I can remember her talking about attending several of those parties. Well, like I said, guys, I can't stress enough. If you have a chance to go see a comet, get out there and see it. Mark Twain frequently predicted that I came in with a comet and I shall go out with a comet, he said. How do you know when a comet has swum into system? Merely by your eye or your telescope, but I hear a brilliant stream of sound that's coming winding through the filaments of majestic sounds, and I know the splendid stranger is there without looking. Mark Twain actually thought he could hear the comet, and he certainly was born when the comet was here, and he died the same year that the comet came back. So he is certainly connected with Halley's Comet. That's why he felt like he could actually hear in his mind the sound of the comet. He didn't need to go ahead and look at it. And then, like I said, probably one of the more famous comets lately is Hale-Bopp, which was here in 1997. Comets are thought to be an omen, usually bad of things to come. A 15th century European prayer was, Lord, save us from the devil, the Turks, and the comet. Amen. Well, like I said, guys, comets have always been viewed as a bad omen. Here's one of them tearing the moon apart. Comet of 44 BC, Julius Caesar was killed. Comet of 1066, King Harold went to war with William the Conqueror and lost, although I would think that William the Conqueror would have taken the comet coming as a good omen since he won. Comet of 1631, Mount Vesuvio erupted and killed a lot of people. Comet of 1665 was a time that London was being decimated by the bubonic plague. Tapestry that shows comets out there. Comets at the nativity scene. Can't imagine what that comet must have looked like in reality. And then, like I said, every time a comet orbits a sun, and it gets smaller and smaller and smaller, then when we being the Earth, run into where that comet was, you get this meteorite shower. And that's why they always appear to be coming from a particular point in the sky. So with that, I'm going to finish. And we'll then go ahead and talk about how we form the solar system next time I see you. See you later, guys.